Hello, welcome to this video series where we are going to talk about industrial machine control. In this video, we are going to talk about how to operate an automatic industrial machine. So, first, we are going to discuss the concept of automation level of a machine. Then, we will invoke the commonly defined modes and their use. Then, we are going to have a deep dive into the machine states and modes as defined by the widely adopted PackML standard. So, let's get started. The automation level of an industrial machine is typically defined by the degree to which human intervention is required for its operation, control, and decision-making. There isn't one single, universally adopted standard, but several frameworks and concepts are used to describe this, often ranging from fully manual to fully autonomous. First, manual machines, whereby all operations, control, and decision-making are performed by a human operator. One could say that the machine acts as a tool. Second, semi-automatic or assisted. The machine performs some tasks automatically, but human input is still required for initiation, monitoring, adjustments, or specific steps. For example, a machine that performs a cycle after a human loads a part and presses a start button. Third, come the conventionally automatic machines, which are the most widely used in the industry today, where the machine performs a sequence of operations without continuous human intervention once initiated. Human oversight is still present for monitoring, maintenance, and error handling. And with the highest automation level are the autonomous machines, also called lights-out machines. These can operate unattended for extended periods, including automatic material handling and tool change if required, autonomous product switching, automatic cleaning cycles, and error recovery. Sometimes they make decisions, adapt to changing conditions, and even self-optimize without direct human intervention for extended periods. This often involves AI, machine learning, and advanced sensing. Now, let us move to the common machine operating modes, which define how an automatic machine behaves and how an operator can interact with it, ranging from full manual control to fully automated operation. Usually, following modes are implemented. First, we have the manual mode, which purpose is to allow an operator to directly control individual machine functions or movements. It's like having direct access to each lever, button, or switch. Direct control means that each action, like move axis forward, turn on a pump, or close a clamp, requires a specific input from the operator. An important aspect in the manual mode are the safety interlocks. The critical safety interlocks, such as emergency stops, guard door interlocks, are still active in this mode to prevent dangerous situations. Another aspect of the manual mode is the reduced speed. Often, a reduced speed called manual mode speed is defined in the machine parameters and is reserved for movements in this mode for safety and precision reasons. In general, this mode is used for setting up the machine, troubleshooting, or maintenance, through performing simple, non-sequential tasks such as jogging axes. The automatic mode lets the machine execute pre-programmed sequences of operations without continuous operator intervention. Once started, it runs through its entire cycle or a defined portion of it. The characteristics of the automatic mode are: first, continuous operation, which means it aims for continuous, repetitive execution of the pre-programmed sequences. Secondly, minimal operator intervention. So the operator typically initiates the cycle, monitors progress, and responds to alarms. Third, the machine runs at full production speed. Operations usually run at their designed production speeds. Number 4 is safety. All safety interlocks are fully active and critical for preventing accidents during high-speed automated movements. And a last word about the automatic mode is: it is used for normal production runs, mass manufacturing, processes that require precise timing and repeatability. The step mode, also called single step mode, allows the operator to execute the automatic program one step at a time. It's a hybrid between manual and automatic, giving granular control over the automatic sequence, which means when the machine completes one logical step or segment of the automatic program, then pauses, waiting for operator confirmation to proceed to the next step. The same speed applying to the automatic mode is also applied to the step mode. The safety rules also are the same as in the automatic mode. Since this mode allows to visually inspect each stage of the process, it can be used for commissioning new machines or testing program changes, as well as for training operators or diagnosing intermittent faults. Also, it can be used for troubleshooting functional issues or verifying machine movements. It is also useful for diagnosing issues within a specific part of the cycle. The service or maintenance mode provides maintenance personnel with special access and control for diagnostic, repair, and calibration tasks. This mode often bypasses certain safety interlocks or allows access to parameters not available in other modes. The access to this mode is usually restricted access, so typically it requires a key switch, a password, or specific login credentials to activate. Caution: some safety interlocks might be temporarily bypassed in this mode, like allowing a door to be open while jogging an axis. This is done under strict safety protocols and often requires a hold to run button or enabling device. Because of the high risk due to potential interlock bypasses, this is the most dangerous mode and requires highly trained personnel and strict adherence to lockout, tagout procedures. That explains why in the service mode, movements are allowed only at very slow speeds. This mode opens usually access to some hidden diagnostic tools, such as diagnostic screens, parameter adjustments possibilities, or the ability to force some inputs and outputs. Cycle mode, or single cycle mode, implies a complete run of the automatic program from start to finish, after which the machine might stop or wait for a new start command rather than continuously repeating. In a lot of systems, automatic might be the overarching state, and cycle start is the command to initiate a single cycle within that automatic state. As with the step mode, the same speed applying to the automatic mode is also applied to the single cycle mode. And here too, the safety rules are the same as in the automatic mode or in the step mode. This mode is used to start a batch process, or to run a single part through a manufacturing cell, or to initiate a test sequence. The specific names and exact behaviors of these modes can vary slightly between different machine manufacturers and industries, but the core concepts remain consistent. They are all designed to provide the right level of control and safety for different operational needs. PackML defines standard modes that describe how the machine is operating, similar to those seen previously. So, according to ISATR 888.00.02, also PackML, the commonly defined modes are: we have the production mode for the normal operation of machine where it is producing a product. You will notice some machine states included as we will discuss later. Then, there is the maintenance mode, which is obviously used for maintenance and service tasks. And the manual mode, as we have seen it previously. Then it defines also a setup or changeover mode that is used for format change, calibration, or setup tasks. There is also a cleaning mode, used for automatic cleaning operations. And for last, there is reserved mode, which can be customized, that is the user-defined mode. The user in this case is the original equipment manufacturer (OEM) or the system integrator. PackML, also known as ISA TR88.002, is currently in its version 3 and has been widely adopted by most of the PLC development platforms through libraries or the like. This standard defines a standard set of 17 machine states that every compliant machine must implement. These states describe the current operational condition of the machine. In the production mode, all the states can be accessed, whereas in other modes, only a subset of them are accessible. As one can see, there are 3 types of states. First type of machine states are the acting states, those represented here with no border. We name starting, stopping, clearing, aborting, holding, unholding, suspending, unsuspending, completing, and the aborting state. What is specific about these states is that they are entered upon an operator or a system-initiated action and exited without operation action. For example, if the current active state is aborted, then the operator needs to trigger a clear command to switch the state machine to the clearing state. In the clearing state, the PLC does the clearing routine and switches autonomously to the stopped state. Second type of states are the so-called wait states, are represented here with a yellow border. We name the states idle, stopped, aborted, held, suspended, and the complete state. What is specific about these states is that they are entered without operator action and exited upon an operator or a system-initiated action. An example for this is the clearing state we have seen. The last type of states is a mixtures of both, that's why they are called dual states. Actually, there is only one state that fulfills this criterion, and it is the execute state. It can automatically be left to completing or upon a hold or a suspend request. Let us consider the stop state as the default state. To prepare the machine for the production, we first need a reset request, which triggers a transition to the resetting state, which then automatically switches to the idle state. From there, we need to send a start request that triggers a switch to the starting state, which if successfully completed, will automatically switch to the execute state. From the execute state, minor internal machine condition or an operator-initiated pause via a push button can set a hold request to pause the execution and set the holding and held state. This often requires minor operator service or a command to unhold. The purpose of the hold branch is to handle minor, temporary internal issues without going through a full stop or abort sequence. A suspend request can be triggered by an external line condition, such as an upstream machine is starved of product, or the downstream machine is blocked or jammed, or a command from a supervisory system. This sets the suspended state. This situation typically clears automatically when the external condition is resolved, transitioning to unsuspending. The purpose of this branch is to manage the production flow on the production line, preventing blockages or starvation. The complete state provides a structured and standardized way for a machine to signal job or batch completion and await further instructions, ensuring a consistent interface across different equipment. The machine cannot simply start a new operation from the complete state. It requires a reset command to transition it into the resetting state and then to idle, from which a new cycle can begin. A stop request is typically a planned, controlled command initiated by an operator or a supervisory system when a production run needs to end in a normal controlled manner. The goal of the stopping state logic is to bring the machine to a safe, controlled stop, allowing it to transition to the stop state, ready for a reset command to start a new cycle. An abort request is triggered by an unplanned, exceptional event or a critical machine fault that requires an immediate and rapid safe shutdown. Regardless of the machine's current state, such as a machine fault or error, a safety system activation, an internal system failure, or supervisory command, emergency. The aborting logic brings the machine to a rapid, safe stop, and the machine remains in the aborted state until the fault is manually cleared and a specific clear command is issued by an operator. In the maintenance mode, the suspend branch is disabled. The same applies to the complete sequence. In the manual mode, the state machine is more simplified and the hold branch is also disabled. The execute state is also simplified and doesn't include the running sequences from the production mode. Now it's time for the conclusions from this video. We have first seen that there is no defined scale for measuring the automation level of an industrial machine. But mostly, we talk about manual, semi-automatic, automatic, or autonomous machines. We have also seen that automatic machine manufacturers usually implement other operating modes than the automatic mode, such as the service and manual modes. We can also keep in mind that operating the machine with open doors is possible in the service mode, but safety has to be granted to avoid injuries. Finally, we have seen how the PackML standard, which is now widely adopted, defines a set of operating modes and machine states and transitions within these modes. With all this said, thanks for your time. I hope you enjoyed the video. Please like, leave a comment, and subscribe for more videos like this one.